Hello, I'm Sabrina Keil and I'm a PhD student at LMU Munich. Welcome to my AGU 2021 online presentation. In the face of climate change, it's very important to look for alternative energy sources. One renewable resource is geothermal energy, which can be used for heating, cooling, or in some cases even to produce electricity. Some side effect, however, is the risk of inducing earthquakes. There are several negative examples that show that this energy source should be exploited with care. One possible way of mitigating the risk and estimating the damage potential of an event are numerical simulations. With such simulations, it's possible to estimate the shaking characteristic of an earthquake in advance, see which areas are most affected, and estimate the peak ground motion. Today I'm going to show you the simulations of the main events that occurred at a geothermal power plant near Munich, Germany. The site is located in the south of Germany in the so-called Molasse Basin, which is a foreland basin north of the Alps. In the Molasse Basin, the crystalline basement rocks are overlain by Mesozoic limestones and Cenozoic sedimentary layers. The limestones form a reservoir at depth which is dipping from the north to the south towards the Alps. In the area around Munich, this reservoir reaches a depth of about 3 to 4 kilometers, which provides sufficiently high temperatures for geothermal energy production. This is the reason why there are many geothermal projects in the area around Munich, which are marked by these red dots. In addition, the natural seismicity in the region is low. However, induced seismicity has been observed at some of those power plants, as indicated by the stars. Most of the events have magnitudes that are very small and are not felt by the population. However, some events with magnitudes larger too have been observed. The site that we're looking at today is located to the east of Munich. The reason why we picked the site is that there are several events with magnitudes between 1.8 and 2.1 were recorded. This allows us to validate our simulations. Another reason is that when the event occurred, the seismic network in the area was quite scarce, and therefore the recorded peak ground velocity might have not been the actual maximum ground motion that the event induced. So with the simulations we will be able to see the distribution of the ground motion and also estimate the peak values to see if the events posed a damage potential to buildings. This geothermal project consists of two wells, one reinjection well TH1 and one production well TH2. They were drilled to depths of about 3 kilometers. Circulation started in 2012, however, no seismicity was observed until 2016. Most of the events have magnitudes less than 1.5, but there was one main shock with magnitude 2.1 in December 2016, which was followed by a larger aftershock of magnitude 1.8. Another magnitude 2.1 event occurred in September 2017. As you can see in the map, most of the events are located close to the reinjection well TH1, which is also situated along this main fault line. In the beginning, there were only few stations installed in the area. That's why the location uncertainty for some of those events is quite large. After the main shock then, a temporary network of 3 additional stations was installed, those PUI stations. That made it possible to locate the events with higher certainty and also estimate a focal mechanism. It is a left lateral strike-slip mechanism with a normal faulting component, which is in accordance to the fault geometry. I'm going to simulate the magnitude 1.8 event because it was one of the best recorded ones, and the magnitude 2.1 event in September 2017 because it was one of the largest ones. For the seismic simulations, I'm using the software Salvos, which is a spectral element code. First of all, in order to do reasonable simulations, we need a detailed 3D subsurface model. So there are a lot of different information that go into this model. First of all, I implement the deep velocity structure from a 3D seismic survey in Munich. I had to extrapolate this velocity structure to the east in order to cover the study area, so there's uncertainty contained in this model. But not only the deep velocity structure is important, especially when we think about side effects, the shallow velocity structure plays a major role, namely the VS30 value, which is the S-wave velocity in the upper 30 meter. For example, a low velocity layer due to soft sediments could amplify the seismic waves. and since we're located in the Molasse Basin, the cities are underlined by sediments. Because of that, there was a microzonation study conducted from Munich to estimate this VS30 value. I take the average value from this study and implement it in the model. Then, for the implementation of the event, the fault geometry and the focal mechanism estimated from the real events is of importance. Also, I consider seismic attenuation, and I take those values that were estimated for the Molasse Basin in an earlier study. We can then set up the simulation. I implement a modeling domain with 8 × 8 km extension and 5 km depth, including all the data that we've seen before. And I place the receivers on the surface. At first, I modeled the event on the 20th of December 2016, which was a magnitude 1.8 event that occurred at 3.4 km depth. It had a mechanism of 64 degrees of strike, 76 degrees of dip, and minus 22 degrees of rake. And in addition, I implement a VS30 layer with 350 meters per second. As you can see, all those event parameters contain uncertainties. So changing those parameters can influence the peak ground motion in the end. I find that the most effective parameters are the magnitude and the depth. Therefore, those values should be estimated as accurately as possible. But also VS30 should not be neglected because low velocities can amplify the waves. Compared to that, changing the event location and the focal mechanism within the uncertainty doesn't influence the peak ground motion as much. Then I also implement a source time function using a Ricker wavelet with a 5 Hz center frequency. Here you can see how the wavelet looks in the time domain, and next to it is its frequency spectrum. At 5 Hz, there's the maximum power. And in that case, I model up to frequencies of 10 Hz because then most of the energy is contained. And this is also a common frequency range for induced events. Modeling to higher frequencies or increasing the size of the modeling domain makes the simulation computationally a lot more expensive. So now let's look at the simulation results for this event. Here you can see the shake map, which shows you the peak ground velocity values at the surface. This allows you to see the distribution of the ground motion and identify the most affected areas. In this case, it would be those yellow regions. For this event, we have real data recorded at the POI stations. So I compare the simulated output with the real data, and based on that, I adjust the event parameters within the uncertainty to find the best match. And these are the final values that I used. With those, I model a PGV value at station POI 1 of 0.6 mm per second, and recorded was 0.65, so we actually got really close to this value. Compared to that, at station POI 3, we overestimate the PGV value. We simulated a value of 0.28 mm per second, and recorded was only 0.11, so this can be improved in the future. Another thing to note is that station POI 1, which back then recorded the largest peak ground velocity for this event, actually doesn't lie in the area of largest ground motion. Therefore, back then, the ground motion was underestimated. So it gets clear why such simulations can be very useful. At this point, I have to take a small excursion. So when it comes to induced seismicity in Germany, one has to take the DIN 4150 into account, which regulates the vibration in buildings. This DIN specifies a maximum tolerable value of 5 mm per second for residential buildings in a frequency range of 1 to 10 Hz. So for vibration amplitudes below this value, damage is unlikely. So now if we compare the maximum PGV value that we got from the simulation, which is 1.57 mm per second, we see that it still lies way below the critical value of 5 mm per second. So this event did not have any damage potential to buildings. In the next step, I want to show you the comparison of the simulated waveforms in blue and the recorded data in orange for station POI 1 for all 3 components. So on the Z component, you can see the arrival of the P wave, and on the horizontal component, the arrival of the S wave. In my opinion, the waveforms match very well. Especially for the north component, we see that the amplitude as well as the shape of the first peaks are matched very well. For the east component, we underestimate the amplitude a bit, and on the sec component we see that the arrival of the P wave is slightly shifted. But in general, I think considering the uncertainty in the velocity model and in the event parameters, we obtain a pretty good match. I mean, better solutions might exist, but with such a waveform modeling approach, it's just not feasible to test all possible parameter combinations because it would be computationally too expensive. The same modeling approach I then did for the event on the 9th of September 2017, which was a magnitude 2.1 event that occurred in 3.1 kilometers depth. I again implement a left lateral strike-slip mechanism with a normal faulting component, and also a V30 layer with 350 meters per second. As source time function, I again use a Ricker wavelet, and I also implement the same modeling domain as before. Here you can then see the shake map for this simulation. In this case, we only have real data at station TH1. I again compare the simulated output with the real data, and based on that I adjust the event parameters to find the best match. And these are then the final parameters that I used. For those, I obtain a PGV value at station TH1 of 0.9 mm per second. And recorded was 0.86 mm per second. So again, we got really close to this value. But also here, station TH1 does not lie in the area of largest ground motion, which is shifted more towards the south. In total, we simulate a PGV value of 2.12 mm per second, which still lies below the critical value of 5 mm per second. So even the largest event in this area did not pose any damage potential to buildings, which is a positive finding. For this event, we also have intensity reports of the population. Those different colored dots show the intensity with which the event was felt. Most of those reports fall in the location of the largest ground motion, so it fits really well. But you have to be a bit careful with the interpretation here, because the location might be biased, because this is also where a small town is located. So that's where most of the houses are and where most of the people live. While in the surroundings there's mainly free fields, so of course we wouldn't expect any reports. But there are also other small towns in the area, and there not many reports have been filed. So in general it matches really good to our results. Then again, I want to show you the comparison of the simulated waveforms in blue and the recorded data in orange for station TH1. On the horizontal components we see that the amplitude as well as the shape of the first peaks is matched very well. But for the sec component again, the P-wave arrival is slightly shifted, so there might be still some error in the P-wave velocity model. This can be improved in the future. But in general I think we obtain a really good match. This brings me to the conclusions. So with our numerical simulations, we were able to get very close to the actual recorded peak ground velocity values. And we were also able to match the waveforms pretty well, considering the uncertainty in the velocity model and in the event parameters. With this, we showed that it is possible to estimate the shaking characteristic of induced events and therefore possibly mitigate the risk of damage. This is useful in areas where we have a scarce seismic network, because then the actual peak ground motion might have not been measured. And based on that, we can then also improve the seismic network. In addition, it's useful for new geothermal projects where we don't have any event data yet, because then we can estimate the risk in advance. With this, I'm at the end. Thank you very much for listening, and if you have any questions, don't hesitate to contact me.